Interstellar objects are already the rarest visitors to our solar system, but days ago, 3I/Atlas's core didn't just crack, it split open with a precision no comet has ever shown. Instead of chaos, scientists are witnessing an ordered fissure, exposing a bizarre interior that defies every expectation of rock and ice. Standard explanations are failing, while instruments hint at energy patterns that shouldn't exist. If comets are supposed to fracture randomly, what's really at the heart of Atlas? And why does this mysterious object seem to be revealing itself right as it approaches Mars? The answers could upend everything we think we know about our place in the cosmos. Solar heating is the great sculptor of cometary fate. As a comet nears the Sun, its frozen core, called the nucleus, faces a sudden rise in temperature. This triggers sublimation, the direct transformation of ices like water, carbon dioxide, and carbon monoxide into gas. The process is violent and unpredictable. Gas jets burst through the porous crust, carrying dust and grit into space. These outbursts build the coma, a glowing cloud that can stretch for tens of thousands of kilometers and launch the iconic tail that streams away from the Sun. The core itself is no fortress. Most cometary nuclei are fragile, loosely bound mixtures of rock, dust, and volatile ices. Their structure is often compared to a pile of dirty snow or a cosmic rubble heap, held together by little more than the cold. As the Sun's energy seeps in, internal pressure mounts. Microfractures spider across the surface. Sometimes a weak spot gives way, a fissure opens, or a chunk breaks free. The result is chaos. Fragments tumble off, gas erupts from new vents, and the nucleus can split in two or more pieces with little warning. Historical records are littered with these messy endings. Comet Shoemaker-Levy 9, torn apart by Jupiter's gravity in 1992, left a train of fragments that slammed into the giant planet 2 years later. 73P/Schwarzmann-Wachmann has splintered repeatedly, leaving a trail of debris that astronomers still track. Even 2I/Borisov, the second interstellar visitor, showed signs of fragmentation as it neared the Sun in 2019, its brightness flickering as pieces broke away. The physics behind these events is well understood. Heat seeps inward unevenly, creating pockets where pressure can build. When the force exceeds the strength of the material, the result is an explosive release. The process is neither neat nor predictable. Each fracture can trigger a cascade, with jets and dust clouds erupting in random directions. The coma swells and dims in fits and starts, reflecting the chaos at the core. No two comets fracture in exactly the same way. Some dissolve quietly, others shatter with spectacular violence. But the pattern is universal. Cracks form irregularly, debris scatters, and the interior is exposed only through sudden, destructive events. The expectation, grounded in decades of observation, is that a comet's death throes are messy, unstable, and governed by the relentless tug of solar heat. This is the reference frame, an unpredictable, disorderly process against which every new cometary anomaly is measured. Atlas refuses to follow the script. Over 30 consecutive days, automated telescopes and space-based observatories captured a sequence that left analysts unsettled. Instead of the expected chaos, ragged fissures, random jets, and a messy debris field, Atlas's nucleus revealed something else entirely. Fracture lines advanced in straight, geometric paths, as if tracing invisible blueprints beneath the surface. Each new crack appeared with mathematical precision, running parallel or perpendicular to the last, sometimes spanning kilometers across the core. There were no sudden outbursts, no billowing dust clouds, no wild jets of gas. The coma, monitored by the Vera Rubin Observatory and confirmed by Hubble, maintained a steady brightness profile. Light curves showed a gentle, continuous rise, not the jagged spikes that betray explosive venting. Polarimetric readings revealed a pattern of negative polarization, a subtle clue that the dust grains in the coma were aligning in a way rarely seen outside the realm of distant, icy worlds. In the control rooms, the reaction was disbelief. Dr. M. Krenker's team at the Rubin Observatory described the event as almost surgical, with each fissure developing at a fixed rate day after day. Internal bulletins circulated, noting the absence of outburst signatures and the eerie regularity of the process. The Minor Planet Center's anomaly logs signed by Krinker flagged the event for urgent review. Avi Loeb, the Harvard astrophysicist who has tracked every interstellar visitor since Oumuamua, put it bluntly: the splitting is too precise, with gas emission zones activating almost according to a schedule. It goes against everything we expect from comet physics. His comment, quoted in academic forums and science media, captured the mood of the moment. This wasn't just an oddity, it was a direct challenge to decades of cometary science. The anomaly extended beyond the visible. Multi-wavelength monitoring, from infrared to ultraviolet, detected no evidence of shock fronts or high-energy impacts. Radio observatories scanned for electromagnetic bursts or plasma signatures, finding only silence. The usual suspects, thermal stress, hidden volatile pockets, micro-collisions, failed to account for the clean, compartmentalized nature of the fissures. Every new dataset added to the puzzle. 30 days, no dust plumes, no debris arcs, no secondary fragments. Just the slow, relentless advance of ordered cracks, exposing an interior that refused to behave like any comet core on record. The question was no longer whether Atlas was breaking apart, but what kind of process could produce such disciplined disassembly. For the first time, the narrative shifted from natural disaster to something that felt disturbingly intentional. The need to test every natural theory became urgent. The mystery of Atlas's core had only deepened. Thermal stress has long been the default explanation for cometary fractures. As sunlight penetrates the surface, buried ice heats unevenly, building pressure until the crust gives way. But when observatories measured Atlas's fracture sequence, the signatures didn't fit. No ejector cones formed. The coma's gas production stayed steady, with no spikes in brightness or heat that would betray a sudden venting of trapped volatiles. Impacts from micrometeoroids were ruled out early. There were no shock fronts, no debris arcs, and not a single radio burst or plasma event that would hint at a collision. Volatile pockets, another usual suspect, tend to rupture with violence. The aftermath is always messy. Dust plumes, tumbling fragments, asymmetric jets. Yet Atlas's cracks advanced in silence without any of the telltale chaos. Neil deGrasse Tyson, interviewed as the anomaly made headlines, cut to the heart of the problem. If we're seeing a naturally occurring fracture, it's the tidiest one in cosmic history. His words echoed through the control rooms. Data from the Rubin Observatory and Hubble confirmed what Tyson described. Each fissure initiated at a single point and extended in a straight line, as if following a plan. The process unfolded over days, not minutes. No random scatter of debris, no secondary fragments, no evidence of explosive force. Spectral analysis of the coma showed compartmentalized outgassing, specific regions activating in sequence, not the turbulent venting expected from ruptured ices. Every mechanism tested, thermal, impact, volatile rupture, predicted chaos. Atlas delivered order. The lack of energy surges, the absence of random debris, and the surgical geometry of the cracks forced a reckoning. Established comet physics could not account for what was unfolding. The search for answers now pointed beyond the boundaries of natural explanation. Hubble's latest measurements put Atlas's core at about 2.7 kilometers in radius, a compact object by interstellar standards. Yet, its mass readings refuse to settle into the expected range. The numbers don't add up. If the nucleus was solid, its density should match that of known comets, or at the very least, fall within a familiar band. But each recalculation, checked by teams at NASA and Harvard, returns a persistent mismatch. The mass is too low for the measured size, or the size is too large for the estimated mass. The discrepancy isn't a rounding error or a calibration glitch, it's a clue. Polarimetric analysis compounds the puzzle. Light scattered by the coma dust reveals a striking negative polarization pattern, a signal rarely seen outside the realm of distant, icy trans-Neptunian worlds. In those objects, negative polarization hints at complex, porous surfaces or a mixture of fine ice and organic grains. For Atlas, the effect is stronger than expected. suggesting not just surface fluffiness but the presence of internal voids or cavities. The dust grains seem to align in a way that betrays more than just a loose surface. They hint at a structure riddled with empty spaces, perhaps extending deep into the core. Attempts to model the nucleus as a solid chunk fail to match the observed brightness and mass loss rates. Only when researchers introduce internal hollows, zones of low density gaps, or even large cavities, do the equations begin to converge. The nucleus then may not be a single block of ice and rock, but a shell or lattice work, its true nature hidden beneath the surface. Every new data set draws attention inward, away from the coma's glow and toward the possibility of a hollow heart. The mystery of Atlas now resides in the spaces that shouldn't exist. The James Webb Space Telescope's thermal mapping campaign began just as the ordered fissures reached their maximum extent. Over a 2-week window, the telescope's near-infrared spectrograph instrument tracked the comet's heat signature across a range of infrared wavelengths. Instead of a uniform temperature gradient, the data revealed alternating hot and cold zones deep within the core. These regions shifted position from one observation to the next, as if some internal process was cycling through compartments. The surface itself stayed cool, but pockets beneath flickered with activity, registering temperature spikes that solar heating alone couldn't explain. Radio arrays joined the effort, searching for electromagnetic signals that might hint at charged particles or magnetic disturbances. Most of the time, the readings matched background noise, but at irregular intervals, brief transients, sharp bursts of electromagnetic interference cut across the data. The signals were faint, lasting only seconds, and never repeated at the same location. Analysts ruled out solar flares or instrument error. Each blip coincided with a shift in the core's thermal pattern, as if the two phenomena were linked. The pattern unsettled researchers. No comet on record has displayed deep interior heat cycling or paired electromagnetic events. The usual suspects, solar wind, cosmic rays, even tidal forces, failed to account for the timing and distribution. Every new dataset suggested something was stirring beneath the surface, something not accounted for in any existing comet model. With the Mars encounter approaching, the question was no longer just about structure. It was about what kind of process could generate energy from within, and what that might mean for everything in its path. Mission planners at NASA and the European Space Agency are not waiting for clarity. With 3I/Atlas projected to pass just inside Mars's orbit in late October 2025, every major Mars mission, MAVEN, ExoMars and Starship, has received new guidance on debris protocols. Internal hazard memos circulate in the background, raising the possibility that if the core's ordered splitting continues, fragments or jets could be released at unpredictable points along its path. The minimum approach distance, 1.67 million miles, sounds comfortable on paper, but the uncertainty around Atlas's internal activity erodes that margin. Even a modest ejection of high-velocity particles could alter the comet's trajectory or pepper Mars's orbital neighborhood with debris. Dr. Yvonne Marshall, navigation lead for MAVEN, has briefed teams on the risk of non-gravitational acceleration, tiny, unpredictable nudges that could send fragments drifting across mission flight paths. The scenario is low probability, but the consequences, damage to orbiters, contamination of sensitive instruments, are enough to keep risk managers on edge. In the control rooms, the anomaly is no longer a distant curiosity. It is a live variable in the calculations that protect billions of dollars in Mars infrastructure. Michio Kaku, speaking to CNN in August, didn't hesitate. This might be our first hard evidence that we aren't the only ones placing objects into interstellar space. The geometry here just doesn't look like what nature cooks up. His words landed with force. While most researchers still lean toward natural explanations, the pattern of compartmentalized splitting and the absence of chaos have fueled a surge of speculation. The idea gaining traction is that Atlas's core could be engineered. A shell, not a solid mass, with internal compartments designed to activate in sequence. Each fissure, each controlled vent, fits a model where the object isn't simply falling apart, but transforming by design. Kaku points to the sequential activation as a possible sign of a programmed process, not random decay. The possibility of a hollow structure, protecting or revealing something within, pushes the debate beyond comet physics and into the realm of technological artifact. For the first time, the question is not just what Atlas is, but who or what built it. Every interstellar object that has crossed the solar system in the past decade has left a residue of unanswered questions. In 2017, Oumuamua swept through with no coma, a flattened shape, and an unexplained acceleration that defied gravity alone. For months, the world debated whether it was a fragment of an alien world, a hydrogen iceberg, or something else entirely. 2 years later, 2I Borisov arrived, hyperactive but by the book. Its outgassing and fragmentation matched what astronomers expected from a typical comet, albeit one born around another star. The pattern seemed set: strangeness, then normalcy. Atlas has broken that sequence. Its ordered fissures, compartmentalized outgassing, and density riddles have revived the sense that something is out of place. Each new dataset, from Hubble's mass estimates to JWST's thermal maps, piles on anomalies that don't fit the template. The glow of the coma, the geometry of the cracks, even the polarization of scattered light, all tug at the boundaries of established science. Is this a random escalation, or are we seeing a progression, a cosmic sequence, each visitor stranger than the last? The question lingers, sharp and unresolved, as Atlas continues its silent transformation in the dark. Only 3 interstellar objects, Oumuamua in 2017, Borisov in 2019, and now Atlas, have ever been recorded passing through our solar system. Unlike its predecessors, 3I Atlas shows a core splitting in ways that defy standard comet physics. Direct imaging, density measurements, and infrared mapping confirm internal structures and energy patterns inconsistent with natural fragmentation. Yet, despite data from Hubble, JWST, and ground-based observatories, scientists cannot fully explain the ordered cracks, unusual heat signatures, or the low overall density. NASA's official position remains that the phenomenon is unexplained and under investigation. As Atlas approaches its 1.67 million-mile flyby of Mars in 2025, mission teams are preparing for possible debris or unexpected trajectory changes. The true nature of Atlas's core, natural or otherwise, remains unresolved. What is clear is that each new interstellar object raises more questions than it answers, challenging our basic understanding of the cosmos.